Hello, everyone. My name is Alaura Cunningham. I am a junior chemistry major at Virginia State University, and I completed research with the Mona collaboration at the Facility for Rare Isotope Beams. The topic that I'm presenting to you today is exploring the physics of neutron-unbound nuclei produced from neon-28 and neon-29 fragment beams. So a little bit of background on the experiment that I completed. The data was collected in 2016 when they were trying to study a 2-neutron unbound oxygen 26. And in order to do that, they had a calcium beam that they bombarded on beryllium targets to produce fluorine 27. In addition to that fluorine 27, there were also neon 28, neon 29, and sodium 30 beams produced. And my portion of the research is looking more into these neon 28 and neon 29 beams. So a little bit about the way the experiment was set up. We had that calcium 48 beam get bombarded onto beryllium targets. And when the secondary beams were produced, they went through this sweeper area. So this sweeper area separated the charged particles and the neutrons. So the neutrons kept going forward and they were able to go into this Mona Lisa area, which was new at the time of the experiment, and it was a new neutron detector. And the charged particles, once they were swept through that sweeper magnet area, they were able to go into this charged ion chamber and be detected there. And so, in combination with this ion chamber and these neutron detector, we were able to measure the position, energy loss, and time of flight of the different beams. The data from 2016 had many different uses. One use was identifying the beams made from the bombardment of calcium 48. Um, this beam identification was able to be done by plotting the time of flight from the A1900 separator to the target scintillator. And that time of flight was plotted versus the amount of energy lost during this first silicon detector. So from there, they were able to see that there was that fluorine 27 beam, neon 29, neon 28, and sodium 30 beam. A next thing that we were able to do from that data was try to find where exactly the different reactions were happening. And we were able to do that by looking at the beryllium target and silicon detector setup. And this setup was very important because we had these three different targets. We were able to have an increased reaction yield. And these silicon detectors being the way that they were, we were able to have this high reaction yield while also having the decay energy resolution maintained. And this was the first time this setup had been used before, and it was ultimately found to be pretty successful in its setup. We were able to identify where in each silicon detector the reaction of neon 28 and neon 29 to fluorine was occurring. We were able to do this by plotting the amount of energy loss in the last three silicon detectors. And we were able to see that on the left side of each of these plots, the left peak represents fluorine beam, and the right peaks are the unreacted neon 28 or neon 29 beams. And we were able to see that in that first silicon detector, there was a little bit less fluorine than neon. As we moved to that second or the next silicon detector, we were able to see that there was more fluorine than neon. And by the time we got to the very last silicon detector, there was an overwhelming amount of fluorine versus neon. An additional piece of information we were able to get from the neon 28 and neon 29 beams were what elements they decayed into. This was done by measuring the time of flight from the thin scintillator to the end of the charged particle detectors. And that was measured versus the energy loss in the ion chamber. And we were able to determine that neon 28 and neon 29 decayed into fluorine, oxygen, nitrogen, and carbon. Another piece of information we were able to obtain is the exact identification of the isotopes in the fluorine, oxygen, nitrogen, and carbon bands. We did this by having a global corrected time of flight that also accounted for nonlinearities in that supermagnet field. And we plotted it again against that loss of energy in the ion chamber. We were able to see that in neon 28, we had fluorine 25, oxygen 22, nitrogen 19, and calcium 16. And in neon 29, we had fluorine 26, oxygen 23, nitrogen 20, and carbon 16. Thank you all so much for listening, and I hope you have an amazing day. Thank you.